Hi, my name is Jim Lydell. I'm with DTE Gas, and I'm going to talk about some exciting new developments in hydrogen production, as well as get you a little bit educated on the different types of methods that are available today and emerging technologies. Some great federal incentives available that are going to really incentivize and move ahead to hydrogen use in the United States for energy and decarbonization. And there's also some solar and other power generation credits that you can stack. So there's options to have multiple credits on one project. Talk a little bit next about what is hydrogen and some of the markets, and then delve in a little more deeply into the Section 47V of the IRA, the Inflation Reduction Act. Talks about some great hydrogen incentives, and then some chemistry. We'll talk about how we use natural gas and how we can make hydrogen, and look at the comparison of those, and show some examples of actual off-the-shelf product. And I've been getting really excited about pyrolysis. Methane pyrolysis basically decomposes methane, CH4, into hydrogen and carbon black, solid carbon black. So there's some definite advantages on the energy and logistics side for that. So I work with DTE. I'm on the gas side of the business. I mean, DTE, formerly Detroit Edison, years ago. DTE Electric handles the electricity for Michigan and the southeast side. They merged, or actually DTE purchased Michigan Consolidated, quite a few years ago, and that territory was all across the state. There's about half of our volume in the southeast, and the other half is out in God's country up north in the beautiful state of Michigan, Upper Peninsula, Grand Rapids, Petoskey, Alpena, Traverse City, beautiful area. So I'm kind of the engineering nerd for this gas sales and marketing group. I support customers and do studies for new technologies for decarbonization to save money, and also some educational stuff in-house, and that's kind of where this comes from. So don't get too tied up in this. You can freeze frame and look at it in more detail. There could be a whole presentation on the tax credits, but I'm going to show you the combination potential of different tax credits on a project like solar and power generation or solar and hydrogen production. There's some you can do and some you cannot. So this is just the acronyms or the tags that I have to show some potential combinations. So for instance, solar photovoltaic, solar electric panels. You can put a solar array in, make hydrogen with an electrolyzer, a water electrolyzer. So you get an investment tax credit or production tax credit on the solar, and the same with the hydrogen gear. The hydrogen equipment can be an investment tax credit of 30-40%, or a production tax credit of up to $3 per kilogram of hydrogen. Quite lucrative and quite helpful. You cannot take natural gas. This is a sustainably sourced natural gas, or certified low leakage natural gas with less methane leakage out in the production side, the transportation side. You cannot, for instance, do pyrolysis or steam methane reforming and take the hydrogen credit and the carbon credit, where you capture the carbon out of the output. You cannot take both of those together. It's specifically disallowed in the legislation. You could also produce solar electricity from a incentivized PV array, big PV array. It's all very scalable. I'll show you some diagrams of how that looks a little later on. And then you can also get the tax credit on the hydrogen. It's 45V. Then you can also put a power producing cogen unit, a CHP, an engine or turbine that could use that hydrogen as a fuel for a very low carbon electrical output with the resiliency of the stored hydrogen. And you can get credits for all three of those in one project. Very helpful. You can put in the cogeneration system and capture the carbon off the back end. If it's large, there's a threshold you have to achieve of a size to do that. Those two credits can be very lucrative together. And then in the 2025, we switched away from this cogeneration incentive. That's going to go away, and then you have to have a clean electric project of any kind, technology agnostic, but it has to have zero carbon. So things like this, wind to produce solar, or wind or solar to produce electricity for hydrogen production, and then a distributed generation, an engine generator or a turbine. These all three can be taken together, and that's good for another 10 years, I believe. And down here, distributed generation, where you have an engine generator off of a sustainably sourced natural gas with carbon capture that'll survive in the future. This could be a whole presentation. I'm not going to dwell on the details, but feel free to contact me if you want to have some more guidance. I am not a tax attorney, just trying to regurgitate some of the things I've been learning. So hydrogen is a great fuel. It's not really a fuel that's out there in nature. It has something we have to make. So it's really more of an energy storage means. It's more competing with a battery. It is a fuel, and if you're going to utilize it, you have to convert your equipment, boiler, engine, turbine, to use hydrogen. In blended quantities, it's not too bad, but to produce or to convert something to use 100% hydrogen is a little bit more difficult, but it can be done. It can be done, and it's being done by many manufacturers. But it is zero carbon. It produces water vapor when it's combusted. It's a very good fuel, but it's very low energy density. It burns much faster than natural gas. So when you blend them together, there's some things to learn. And hydrogen is very difficult to compress. So transportation over pipelines or trucks can be troublesome because of its low energy density and difficulty to compress. Very, very expensive to do that. And it has issues with steel and embrittlement. You're going to have different heating values if you have blends. So it's complicated, but I'm a big fan of distributed hydrogen. Let's produce it out in the field at the point of use. I'll talk more about that later. So gray hydrogen, if you use natural gas and use steam methane reforming, that's called gray hydrogen. You let the CO2 escape. It's fairly CO2 intensive, but that CO2 could be captured. There's these amine processes or other carbon capture processes that are available today. It's nothing in the future. It's available today, but it costs more money. And then you scrub out the CO2, similar to a scrubber, like a NOx scrubber. If you've seen a urea-based scrubber for an engine system that reduces the NOx, it's going to be fairly similar, but now we're getting rid of the CO2, and that's blue hydrogen. Green hydrogen, I'll skip over to that. That's renewable energy, renewable wind or solar into electrolyzer to make hydrogen from water. That's green. Pink is the same thing, but maybe nuclear power. And turquoise is this pyrolysis, where you thermally decompose methane, natural gas, into solid carbon and no CO2, no gas, just a solid carbon, and then the hydrogen. So the tax credit, it's really the $3 here. That's the holy grail, quite lucrative, is for the green hydrogen. Although I believe we can get there with pyrolysis as well, and I'll talk to that in a moment. If you missed that target, the target is 0.45 kilograms of CO2 or greenhouse gas equivalent per hydrogen kilogram produced. If you don't make that, you've dropped down to $1, and there's some other threshold as well. So the methane leakage in the whole food chain, using this Argonne National Lab GREET model, in the bill they call out a methodology that'll be used to calculate leakage from the wellhead to the pipeline, all throughout, wheels to well to wheels analysis. But we're talking about from the wellhead to your project site. And the methane leakage is really important. We have to get low leakage product for these things to get to the $3. There are certified, sustainably sourced, or responsibly sourced products out there that are third-party verified of low leakage. I believe we can get to this $3 credit if we use those products. But we have to stop the leaks. In the previous bill, the infrastructure bill, there are some carrots and sticks in there that were forcing the gas industry to really get more aggressive with stopping leaks. We have to stop methane leaks. That's a requirement. With or without all this I'm talking about, we have to get rid of the methane leaks. Here, so looking at 1 MCF, if you're paying a natural gas bill, you're either going to be charged a CCF, 100 cubic feet, or 1,000 cubic feet, which is an MCF. When you combust an MCF, it's about 56 roughly, 55.8 kilograms of CO2. And if you pyrolyze it, you get about 5 kilograms of hydrogen. That's just the decomposition of the CH4. There's four hydrogen molecules to make about 5 kilograms per MCF. So using the carbon sequestration section 45Q, there's two provisions. If you sell the CO2, you get $60 a ton. That's a metric ton, 1,000 kilograms metric ton, or 85 if you somehow sequester it. There's a cost and some unknowns on that sequestration, so I don't have the knowledge to speak to that. But these are the ranges here: $3 or $4 per MCF of value in the carbon capture side of the business. If you're to make hydrogen and get the $1 credit, don't quite get clean enough, you can get $5 per MCF, which is much more lucrative to make the hydrogen. And if you get the $3 threshold, that's even better, about $15 per MCF of gas purchased. So imagine buying gas at $3, $4, and then having a project that'll then create hydrogen, which is a product, carbon black, which could be sold as well, and then $15 in a federal incentive. That incentive lasts for 10 years. So this hydrogen action plan, relatively new, data from 2023, looks at the carbon intensity produced from steam methane reforming. The first column is steam methane reforming. with no carbon capture. Just let it go, let the gas go. So the majority of it is stack emissions, but there's natural gas emissions, the yellow from the pipeline and the wellhead. All that stuff is fairly significant. And then the grid, using a standard average carbon intensity in the grid for electricity. That's what builds up this number. Carbon capture, you can remove some of that, but you're not going to get to where we need to be. Well, actually, this is the one. So this one is still at 4.6 kilograms of CO2 equivalent per kilogram of hydrogen. But the methane leakage, if you could get a really sustainably sourced product here and then use renewable electricity, this 1.2 and 2.9 can be brought down to next to zero. And so that'd be solar or wind electricity, and then potentially you could blend in a little bit of renewable natural gas. So I see it's within reach, and some of the companies are saying they can do it. To further this discussion, feel free to click on this link down here. There's an article from Recharge News Online that talks about this math and this equation to get to the 0.45 kilograms of greenhouse gas under the GREET model. So it is doable. It is doable. Keep moving along. Hydrogen production today. This EPA data, I believe this came from the same document that I referenced earlier. This is where it's coming from today. Steam methane reforming without carbon capture is predominantly the source of all hydrogen. Going to petroleum, ammonia, methanol. So ammonia, the Haber-Bosch process to make ammonia, it's NH3. That's enabled humankind to exist today on this planet the way we have. That's the most prolific, most important to mankind, I believe, of all chemical processes. And it takes hydrogen. So that hydrogen is typically coming from natural gas. CH4 into hydrogen into NH4, nitrogen from the air. Sometimes there's hydrogen produced from an industrial process, and that's utilized on site. But electrolysis is quite expensive and new, and that's the green hydrogen. That's up and coming, but it's quite expensive, and it's going to take some time to grow in the marketplace. This is where you're going to see hydrogen being produced and utilized today. There's hydrogen pipelines in the Gulf. This is the oil and gas industry, and there's some spots around the country. But let's talk about some chemistry. So natural gas can be burned in your boiler or in your furnace or in your process. That's what we're all used to. And then steam methane reforming, which is what we saw was the predominant source of hydrogen. I'll show you that. And then electrolysis. My original thesis for this presentation was to compare reforming SMR, steam methane reforming, with electrolysis. But I've been getting really excited about this pyrolysis opportunity. I think it's got a lot of logistical and engineering benefits. So the methane, the CH4, I'm going to use the unit of 1 MCF, so 1,000 cubic feet, using the density numbers here in the bottom right. 1 MCF is about 20 kilograms of mass, 20 kilograms of natural gas. I'm going to assume it's CH4. So when you burn it, you get oxygen in the air, and it produces heat. We're looking for heat. That's fuel. Produces a fair bit of CO2 and a fair bit of water vapor, a lot of water vapor. So carbon dioxide is about 75% oxygen. So if you're going to capture CO2 and then compress it, liquefy it, store it, pipe it, whatever you're going to do with it, sequester it, it's about 25% or approximately 25% carbon. The rest is all oxygen. So that's coming along for the ride. That's a lot of logistical nightmare if we're going to capture some substantial quantity of our emissions. SMR, steam methane reforming with water gas shift. Actually, it's the reforming process, and they inject some steam. So there's some energy and some CO2 emissions in the steam boiler process. It looks something like this. With the water injected, it's going to produce more hydrogen, about 10 kilograms per MCF. And then the methane pyrolysis. So you're basically cooking it. There's different methods. There's catalyst methods, fluidized beds. There's these bubble columns with the liquid metal or molten salt. Plasma, microwave, and other forms of plasma to basically heat and decompose the methane directly into solid carbon. I'll show you some pretty cool animations, or not animations, some examples of that. Some cartoons that kind of show these processes. And your boiler is going to burn methane and combust it with air. Air is like 20-some% oxygen, and the rest is nitrogen and other small amounts. So that produces the CO2 and water. Steam methane reforming, I'm not going to dwell upon this. I don't want to take too long, but the exciting part to me, I'll talk more in a moment about this solid carbon, which has a value. There's some potentially valuable components in there, like fullerenes or nanotubes or graphene, that might add value to the whole process. If not, it could be sold in bulk to tire manufacturer, maybe process it into some biochar for putting in agricultural uses. There's a lot of uses of carbon black, but if we start using this pyrolysis a lot, there could be a deluge of that on the market. How does it compare to electrolysis? So electrolysis is much more energy intensive. The water molecules is not a fuel. It's CH4, methane, natural gas is a fuel. It's got a lot of energy waiting to be burned or utilized. Water is not a fuel. It's a happy little molecule. It doesn't want to change. It's very stable. So you have to forcibly split apart that, and it takes 7 or 8 times the amount of energy to activate that separation of hydrogen and oxygen. So I think you're going to see a lot of it. That's where that $3 credit was really designed for green hydrogen. This is the green hydrogen, and you're taking a lot of electricity. Has to be from solar or wind. You can't. I mean, if it's from nuclear, that's great. I think nuclear has a place in our future, but the grid has a lot of carbon in it. So if you're just pulling the electricity off the grid, this may not be the cleanest, greenest process. But a pilot project, a utility pilot project at a customer site might look something like this. You got the solar, and you could make DC electricity go straight to the electrolyzer, but that would be a custom system that doesn't exist in the marketplace today. So it'll probably be a conventional inverter to the grid interactive type system. And then we'll pull AC power to the electrolyzer. It does take a fair bit of water. So if you're going to produce massive amounts of hydrogen, you're going to need some pretty serious water supply. So doing the desert might be a challenge. And then it could be blended with natural gas. It could go into an engine generator. But this is the type of pilot project that I've been preparing to shop around to see if any customers would like to test it out. We could do it at one of the DT sites as well. A lot of companies make stuff off the shelf. I am not promoting or endorsing any particular company. I'm just showing you a handful of pyrolysis companies. There's a lot of small startups in that realm. I'm going to show you some information from Monolith and C0. They're the 2 larger ones that I've got some good graphics from. SMR, these are very, very mature technologies, very mature and very well utilized. Air Liquide, Zeebec, many others, but I just threw a few in here. And then electrolysis, Nel used to be Proton On-Site Energy, now it's Nel. Hydrogenics, I believe, is bought by Cummins, and so I'll show you some Zeebec examples. Like I said, I'm not endorsing anybody, but these are all scalable. You can get really small units to really big containerized large units that produce a lot of hydrogen. And they can be stacked together in an array in a big plant. So there's the great ability to scale both the solar photovoltaic side, 1 panel to 1 million panels. I mean, it's scalable on the hydrogen and the power generation side. Wind power is even cheaper, and that's an option, putting these things out near wind farms. So, and you're basically making a storage of energy. You're storing it in the hydrogen as a chemical fuel. Toronto, Enbridge Gas has put a cool little project in there. I believe they started blending in the hydrogen into the grid to have a test pilot installation of a hydrogen blending opportunity. SMR, steam methane reforming with water gas shift. Here's some examples and some sites that give you a flavor of what it looks like. 2 containerized systems with some coolers that are spread apart. Let's talk a bit about pyrolysis. I've got 2 video clips. They're 2 minutes each to kind of get you up to speed on what this might look like. This C0 technology is using a molten salt bubble column. So the graphic on the side here is a potential very, very large facility, commercial scale facility. And they're saying here the CO2 is 27% carbon, the rest is oxygen. So why make CO2 gas when you can do it this way? Let's take a look.
We describe what we're doing at C0 as turquoise hydrogen, because it's kind of a combination of both blue and green in that it's low cost and low emission. C0 has developed a technology for removing the carbon in natural gas. Natural gas is a hydrocarbon. It's made out of hydrogen and carbon. And what we do is remove the carbon. And so we pull out the solid carbon out of the hydrogen that we produce, and there are no direct CO2 emissions because anything that would have been CO2 is instead solid carbon. If you want to get hydrogen from water, it takes 7.5 times as much energy to go pull hydrogen off of oxygen by splitting water as it does to pull hydrogen off of carbon through our process.
The way C0 achieves it is using molten salts. It has a big chamber full of salt that is heated to a very high temperature.
So this is an example of one of our laboratory scale reactors. So right here we have a very high temperature, around 1,000 degrees and slightly above molten media column.
And it bubbles natural gas through that chamber, leaving behind carbon in its elemental form, and hydrogen is a gas that can be trapped and sold.
If we're successful, we're producing piles of black carbon that ultimately gets sequestered back into the ground. You can think of it almost as pre-combustion carbon capture. Rather than ending up with CO2 that you have to concentrate, compress, put into a pipeline and inject it underground, we pull it out ahead of time as a solid that's much denser, and you can move around with conventional solids handling equipment and dispose of.
Just like green hydrogen, the success of turquoise hydrogen will ultimately come down to cost.
$1.50 per kilogram of hydrogen is our target for doing this at very large scale. If you can be $2 a kilogram or less with, very low to zero CO2 emissions, that's kind of a game changer.
All right. Monolith is another more established pyrolysis company using a plasma system, and they're installing a very, very large site out in Nebraska for ammonia production. And I believe this is operational and they're expanding it, I think. It's a Olive Creek project out in Nebraska.
The key to meeting the 2050 decarbonization goal is clean hydrogen. This solution provides the high energy needs for a wide array of industries and categories. Traditionally, there have been two methods for producing hydrogen. The first, steam methane reforming, or SMR, although affordable, releases 11 tons of CO2 in the atmosphere for every 1 ton of hydrogen produced. The second method, electrolysis, is a low-emission solution but not as affordable and requires 7 times the electricity than the new third method for producing hydrogen. This method, methane pyrolysis, has been perfected and made commercially viable and scalable by Monolith, and is the only low-cost and low-emission solution to create carbon-free hydrogen. Using 100% renewable electricity, methane pyrolysis cracks the natural gas molecule using heat, not combustion, so there is no release of CO2. And in the very near future, through the use of renewable biogas, it will not simply be carbon zero, but carbon negative. 2050 is approaching. Without an affordable and at-scale carbon-free hydrogen solution, the world will not meet its emission goals, which is why clean hydrogen, produced by Monolith, will lead the way to the energy transition.
Monolith. So they do believe that they can get to the 0.45. So this is from their literature, with their process here in the middle, saying that they can reach that $3 credit threshold. It's pretty cool. And electrolysis at zero. On the left here, the columns are steam methane reforming with and without carbon capture. But exciting, and I think as an engineer, this is very true. So if you use renewable natural gas from manure or biosources, some biogenic natural gas, you could actually make this system a carbon negative opportunity to produce carbon credits for someone else. That's really exciting. I mean, this is not greenwashing. This is a true opportunity. So distributed hydrogen, I think, has some major benefits. The difficulty of compressing and transporting, God forbid, liquefying hydrogen makes it really challenging to move around. It's much better to make use of this multi-trillion-dollar natural gas infrastructure that we have developed over many decades that is very reliable, very reliable. Resiliency and looking at all these power outages across the country makes you wonder if electrification is really going to ever have the resiliency and the safety that we need. I think some combination of these things might require us to do some distributed hydrogen technologies. Anyway, take a look at these bullet points. Steam method reforming is king right now, but I think the pyrolysis, as these companies develop further business models, might just be the way to go, because of the fact that it's solid carbon and it's immediately sequestered. Once you pull that carbon out in your process, there's no worry about it escaping back the atmosphere. It's sequestered right then and there. That's really exciting. It's a really good tool to decarbonize our natural gas industry. But one thing that I should mention is that it's going to take at least, or approximately, I'm working on what this might actually look like, but about double the gas supply to the customer. So imagine, as a gas utility, if you were serving a boiler or an engine, that heating load, that BTU energy requirement, through the pyrolysis process, which is roughly 58% efficient, you're leaving some energy in the carbon, so the carbon is not combusted. There's energy lost there, and there's the activation energy for the process. You're going to have to supply about twice the product, twice the natural gas to that process. But the tax credits pay for it all completely, so it's a lucrative opportunity while you're selling twice the product. That's amazing. For folks that don't want to use natural gas, that might be counterintuitive or not desirable, but for a gas utility, you're sequestering the carbon, so you're decarbonizing your customer site and selling more product. That's just an amazing opportunity. I did some numbers here looking at the 10-cent electricity. I'm using a number from a friend of mine who's a chemist that has a pyrolysis process of a fairly low 3.8 kilowatt hours per MCF processed. That may be too low, so even if it's more than that, I think we can still make money on the process, but there's no value of carbon here. But 10 cents a kilowatt hour for green wind or solar power, and then that this amount of electricity. But the electricity isn't really the driver. It's the natural gas cost. So if you get the $3 credit, if we can make the, maybe blend in a little bit of renewable natural gas, which will increase your price, or get this responsibly, sustainably sourced, certified, low leakage natural gas, and with whatever you need to do to get that 0.45 in your process and your fuel supply, the money involved is quite lucrative. So if natural gas is in the range from $3.50 to $5, you can still get a profit if you have the $1. So if you miss the target, I think there's still an opportunity. If you were to sell the carbon for $5 a ton, just some nominal made-up number of $5 a ton, it improves the ROI, and the value chain is a little bit better. The value proposition is a little bit better. And then once this 45V goes away, I truly think there'll be a carbon tax or some kind of a tax and dividend or cap and trade style thing that will force people to get off carbon. A lot of companies are making commitments to decarbonize today, and they're looking at electric technologies. But if they have a process that needs natural gas, this could be a solution. So this is just the whole economics based upon the carbon sale of $5 a ton only, and it still makes a good value. So to conclude, SMR is king today. It's the dominant form of hydrogen production. But solar electrolysis is up and coming. It works well. It's very scalable. And I think keep an eye on the pyrolysis opportunities to see if these companies can show some success and show some demonstrations out in the field. And I think that can be made to do garner the $3 credit with some magic on the fuel supply side that needs your attention with these other products. And then I think gas utilities should support these technologies and really further the efforts to commercialize the pyrolysis. Thank you for your time, and feel free to contact me for any questions or follow-up. And I hope we have a green, sustainable future. Thank you.